some subcomplexes that arise in homogeneous nilpotent Lie groups. So to be honest, I don't know how insightful this is going to be for people that have not seen any kind of subcomplexes before. But I'll try my best. So the idea, what I would like to kind of convey is that historically there's been a construction called the Rumin complex on especially sub-Riemannian stratifiable Lie groups, also called Carnot groups. And this has been kind of it was very popular on the Heisenberg group because it's very, very nice on the sort of like very simple nilpotent Lie groups. However, it doesn't really generalize that well on sub-Riemannian manifolds, and so it was kind of set aside for a while, and then using the BGG sequences, some other people constructed other subcomplexes, and actually together with Veronique Fischer, we kind of checked both constructions, and in this sort of setting, so homogeneous nilpotent Lie groups, the two coincide. Okay, so this is like the story of the talk. Hopefully some of the computations will also stick, but yeah. So we're going to start with what is known as the Chevalier-Eilenberg complex. So this is usually, you see this if you do the algebra cohomology. Then we're going to very quickly see the Rumin complex, and then maybe the BGG sequences construction is going to be more, I don't know, approachable. So, okay, so we're going to be working with a simply connected nilpotent Lie group. So, at the moment, I'm not requiring anything on the homogeneity, so it's going to make sense what homogeneous means in this case. I'm going to introduce that later. So for the notation, so this is the exterior derivative, so the RAM differential, whatever you want to call it. So the K here denotes the degree of the forms that it's going to act on. So this is the formula you get also on Wikipedia. So this is the usual kind of exterior derivative. So when you do like differential geometry as a course, usually you see this, and you kind of missing the second addend. So why is that? Because usually you work with things that don't have a complicated algebra. So this is always going to be 0. Actually, in this case, for the Chevalier-Eilenberg complex, this is the crucial bit. So as you can see, this is the first addend involves differentiation, the second one doesn't. Okay. So I think this was kind of mentioned in the previous talk as well. So in a Lie group, we have a product, and I don't really know why, but we kind of like left translations more than right translations. So we define the left translation map, and then we can define the subspace of what are known as left invariant forms. So those are the differential forms that stay the same when you pull back through the left translation. So you can think of those as like constant coefficients in like the RAM complex on Rn. So because the pullback is compatible with the exterior derivative, as something you see in differential geometry, then if you apply the exterior derivative to left invariant forms, then you still get left invariant forms. So it makes sense to stay within left invariant forms. So for maybe it's clearer if you identify left invariant forms with covectors of the Lie algebra. So you can think of like the Lie algebra as the tangent at the 0 point, basically, and then you kind of let translate, and it's going to be copies of the same things everywhere. So in this case, the Chevalier-Eilenberg differential is going to be just the d applied on the left invariant. So you can think of it as if it has constant coefficient, then if I differentiate, I get 0, right? So this is why this is the only thing that is left. So this is a complex, so you can compute the cohomology of this complex. Okay, so we also need a codifferential, so we're going to define this. We fix like a scalar product on G, and by duality you have it on G star as well. And then you extend it to covectors in general. So just for the notation, we're going to use PRS as the orthogonal projection on a subspace. And the thetas are the dual, so this is the dual basis, which means that theta I applied to xj gives the Kronecker delta of ij. And then one can check that actually this set of covectors are actually an orthonormal basis for the space of covectors, right? I don't know if this is very, very easy or kind of already very boring. Okay, so we define the codifferential using this scalar product as the formal transpose. So interestingly, so for the notation, because k, d, when we were doing d0, d0k goes from k forms to k plus 1 forms. So when you transpose it, it goes from k plus 1 forms. So this is why. So d0k goes from k plus 1 to k. And also d0t, so the transpose twice is 0. Okay, this is, within this talk, the Hodge star is kind of, it's not that useful. So if you've seen this before, then okay. Otherwise, it's a way to kind of express, think of it as it's a way to express the transpose, so the codifferential in terms of the d0, okay? And then the interesting thing that we're going to use is that the image of this d0 transpose is equal to the orthogonal complement of the kernel of d0. These 2 points are actually the useful bits here. Okay, so what are we going to look at here? So we consider this subspace. So what we need to check here is that this is a fairly intelligent thing to do, okay? So this is actually a complex. So you can check by the properties of the d0 and the d0 transpose that if you apply d0 on f0, then it's still an element in f0. So this stays inside. We know already that d0 is a complex, so d0 squared is 0. And we can compute the cohomology of the d0 when restricted to f0. Now, the interesting thing is that by the properties of the d0 and the d0 transpose, so the kernel of d0 limited to f0 gives the image of d0, which is the same as doing the image, right? Which means that actually the cohomology, so this is all to say the cohomology here is going to be trivial everywhere, okay? So it doesn't give you any information about the Lie algebra that you're considering, basically. So it makes sense to discard F0 and focus on E0. So the orthogonal complement of this F0. And you can see that actually this is the expression, and yeah, so this is the same as saying this is the image of D0 orthogonal complement by what we were saying before. If it makes sense. So this is the same as saying this is actually the cohomology of the D0. So, does it make sense? So, this is the same as this, right? So, if you discarded this and put in this, it's literally the cohomology of the D0, not just as a quotient, but as a subspace. So, the question here is, so we start from the Durand complex, and we want to enter this E0, D0, okay? So, oh sorry, that's actually my iPad. Okay, so how do we project onto E0? So usually, what Rumin has done is to construct a partial inverse of D0, and we'll see that this BGG construction uses the Laplacian, like the box Laplacian of D0. So let's have a look at Rumin's construction. So basically what this is when restricted to the image of D0, I can construct the inverse of D0. So this is just what it is. So this is D0 inverse. And the nice thing is that when you do D0 inverse after D, then it's the same as taking the projection onto the image of D0 transpose. And D0 after D0 inverse is the projection onto the image of D0. You check this. Okay. So then if you consider this operator, then this is a projection onto the image of R0, which is the kernel of D0 intersected with the kernel of D0 inverse, which is exactly E0. This is kind of boring things to check, and it's probably confusing if you've never done the computations before. But basically, trust me, if you do this, then you're projecting exactly to where you want to project. So instead, with Daven-Haller's, so you have this operator. So it's a symmetric operator by the definition. So you can decompose, like the spectral decomposition of box 0. And actually, each pi lambda is an orthogonal projection onto the eigenspace of each eigenvalue lambda. I don't know, this should be kind of fairly okay, right? Okay, so in particular, we're looking at lambda 0. And so for lambda equals to 0, we have the orthogonal projection onto the kernel of this box 0, which is exactly E0. Okay, so we have two projections, which are the same projection. So I feel like this, if you've never seen this before, this is more easily understood. So you have box, and then you project onto the kernel of box, which is this subspace. In the other case, I have to construct this D0 inverse, which kind of coincides with D0 transpose, but yeah. So you have either this projection that you're considering, or you consider the pi 0. Okay, so we have this projection equal to pi 0 or equal to r0. Okay, so everything works fine. So we were restricting ourselves to left invariant forms for now. But if you think of smooth forms as just the C infinity G module over there, so then everything we've said so far extends to smooth forms. And then you also consider the L2 inner product. So I just introduced this because we had the formal transpose for D0. This is the formal transpose for D. So this is the complete D. And you just do the codifferential for the whole D, right? And this is the definition. Okay. So this is for the D transpose. And now everything we've said so far for left invariant forms. So we had the D0, D0T, D0 inverse, and box 0. They extended to smooth forms. So now, before we were considering E0 and F0 as subspace of left invariant, now it's on smooth forms, but it's exactly the same thing, okay? Just the coefficients are no longer constant, okay? Okay. So, now what we've been saying works for any Lie group, I guess. Now we're considering homogeneous nilpotent Lie groups. So G, what it means is that G admits a family of dilations that can be seen as a matrix operator as like the diagonal. So these eigenvalues for the morphism A, these are called the weights. Now, this notation is just, you may have like two weights that are equal to each other. I'm going to use W for the weights without the multiplicity. So these are all different, okay? Just the notation. So if you think of like a Cardinal group, like a two-step Cardinal group, then you can consider the dilations that give the stratification, and you can fix the first one to be 1 and the second one to be 2, for example. It's not necessary for this to be 1 and 2. You can change them. But that's not the issue. So, and as long as you can put what usually are known as homogeneous dilations in this sense, then it's called a homogeneous nilpotent Lie group. Usually, so these don't need to be integer for us. Usually they're taken to be integers, but yeah. Okay, so this, why are we taking this homogeneous kind of situation? Is because this reflects well onto the Wj eigenspace for A. A was the thing that defined the dilation. So it behaves well with, so you have like a direct sum decomposition of the Lie algebra in terms of these eigenspaces, and they satisfy this inclusion. So it's a homogeneous filtration. Okay. We're not requiring equality at any step, and so we're not requiring the first layer, for example, to generate. I don't know if it makes sense, but like for some people it may ring a bell. So we introduced the concept of weights. So these, this is left invariant one form. Basically, if it's the dual, if this left invariant one form is the dual of something that stays in the level Wj, of the Lie algebra, then we say that it has weight Wj. So you have a direct sum decomposition of G, which reflects into a direct sum decomposition of G star. And if an element belongs to this G star Wj, then it has weight Wj. And this extends in general to two forms. You just sum the weights. So for a K form here, you just take the sum of the weights of each form. Okay. And then you extend it to smooth forms, right? So why are we, so this is in Rumin's kind of idea of construction. So why are we considering weights? Because there's a very nice way of expressing the action of D and D0 in terms of the weight. So we look back at D0 and we actually have the D0 commutes with the dilation. So it actually means that the D0 preserves the weight. So this probably is better seen by the definition of the D0 when you had that, where is it? Somewhere? Yeah, so there is the Lie bracket here, right? So this weight that behaves well, so the weight was very much linked to the action of the Lie bracket. So the D0 preserves this weight. So this is crucial in Rumin's construction. So the algebraic operator D0 that doesn't differentiate actually preserves the weight. And actually, when you remove the D0 from the whole exterior differential, then it strictly increases the weight. Why is that? Because D actually, the D0 is actually the action of D on the left invariant form, which is exactly the action of the D0, okay? So we have that D0 keeps the weight constant, and D minus D0 increases the weight. So now these are the two lemmas that we're going to use throughout. So if B is a linear operator that strictly increases weights, then B is nilpotent. Why is that? We're working on a finite dimensional Lie algebra. The number of weights is finite. So if you increase the weights, there's going to be a certain point at which you finish the number of weights, okay? So if it increases the weights, then it's nilpotent. And lemma 2 is if you have an A0, so A0 keeps the weight constant and B is the nilpotent one, so it increases the weights, then we introduce A, which is A0 minus B, then this is invertible and its inverse is expressed through the Neumann series, basically. So this, you don't need to like visualize this, but just we're going to use a lot the fact that if you have a linear operator that keeps the weights constant, something that is nilpotent, and in particular it increases the weights, then the difference or the sum is invertible, okay? So we're going to use this. So if we consider B, so this is D0 inverse after D minus D0. So keeps the weight constant. So if D0 keeps the weight constant, then D0 inverse keeps the weight constant. So this whole thing increases the weight, hence is nilpotent. So the identity, so this is going to be my A0 minus B, yeah. So this is invertible. So I can construct the inverse. And so what Rumin did was to construct this pi as this operator. So these first 2 points is to say this is well defined, and it's a projection onto this subspace of smooth forms along E. Okay. Now, magic happens, and then I define pi f to be this projection pi, and pi e to be I minus pi. Now, what Rumin found out, let's say, is that pi, so the RAM complex splits into E and F. So E is the projection of pi E, and F is the projection of, it's the image of the projection pi F. And if you define this operator like this, so pi 0 was the projection onto E0. Pi E is this pi, then you have the D, very complicated thing. Then actually dc squared is equal to 0. dc, yeah, well, yeah, okay. And so the idea is that you're acting, this dc takes a smooth forms, projects down onto E0. So you can think of this dc as starting from E0, and then it ends up back again on E0. And Rumin said, oh, look, this computes the same as the RAM cohomology, right? So, long story short, we created a very weird pi E using a lot of operators in between, and I go from E0 to E0, and I compute the RAM cohomology, okay? So this is Rumin's construction. Okay, hopefully it's not too boring. So, now let's have a look at the BGG construction. So, we're considering box. Now, this is not the de Rham-Laplace operator, because the de Rham, if you've ever seen it, this is D star, D star, D. In this case, it's D, D0, the codifferential of D0, and then the codifferential of D0, D, okay? So usually, okay, yeah, there's supposed to be a D0 here, okay? So so these are both the Rham-Laplace, but I meant to write a D0 here, okay? So this is not symmetric, right? This is to compare this with this that was symmetric. So I cannot do the same reasoning as before with the spectral decomposition. However, I can split it. So I can find a box 0 here, and then this is what I'm left with, right? So I cannot do the spectral decomposition. However, if I remember, so the spectral decomposition, so this pi 0 can actually be defined in this way using like the residue theorem. So my best guess of projecting onto the kernel of pi, so this time before I was projecting on the kernel of pi 0, of box 0, this time I want to project onto the kernel of that thing. So my best guess is this. Now the question is, does this even make sense, this Z minus box inverse? And actually it does. So, because basically if I remove the box 0, this thing increases weight, right? It's always the same two lemmas that I'm applying. So strictly increases the weight, so it's nilpotent. This thing keeps the weight constant. So I introduce my A0, my A, and then I know that Z minus box is invertible. So it makes sense, okay? And then I also, you find out that actually it's a projection. So before I had a pi 0 to project, and now I have this p to project. And this is going to be useful later. So if I can find the pi 0 inside p, okay? Somehow. So just in the same way I found a box 0 inside box, I can find a pi 0 inside p. So if I consider p minus pi 0, then it strictly increases the weights, which is going to be useful later. Okay, so let's consider this operator, okay? Why am I considering this? It's a good question. This is invertible, and this is gonna be useful later. So why is this invertible? Because if you do L minus I, this strictly increases the weights, and then you use the Neumann series, so it's invertible. Oh, you can use the lemma. Yeah, you also have the lemma. Yeah. So I have this L. It's P. So the only thing that I can mention maybe is that you have almost two projections, one after the other, because P kind of is an extension of pi 0 somehow. And so we're ready to decouple the de Rham complex in the BGG sense. So I use this operator, and I define D. Now this is so, okay. So basically I have L inverse DL, okay? Now, this I didn't change anything, right? I just sum and the pi with the pi 0 and subtract with the pi 0. Yeah. 5 minutes? Okay, so I just decouple this with projecting on pi 0 first and projecting on projecting on E0 and then projecting on F0. I want to introduce D. So this is the same thing. You just check that if you introduce pi 0, it doesn't change anything. And the same thing goes for C. So I'm just dividing this L inverse DL into the sum of D and C. And actually, you see that they both behave very well. So this D stays in E0 and this C stays in F0. And they're both complexes, right? So D squared and C squared are both equal to 0. Then you show that actually this, so I have the F0 with C, and it's conjugated to, what did I use? To F0D0. Do you remember F0D0 at the very beginning? It had trivial cohomology. It was the useless one. So actually, when we decouple this with the C, useless. So let's do the other one. So for the other one, you actually see that it's conjugated to the de Rham complex. So it computes the same cohomology. So you have E0 and D, and it computes the same cohomology as the de Rham cohomology. So, conclusion, we're left to check that actually, so the E0s are exactly the same spaces, and then we have a pi E and a P. You show that these two coincide, and so when you go and decompose D, so this was the expression, the weird expression of capital D, and you check that this is actually pi 0 D P pi 0, and when you compare it with DC, because we just proved the pi, e, and p coincide, then these two are the same. Yeah, it's a lot of believing. Now the question is, and so what? So the thing is, the Rumin complex was useful because it's a sharper subcomplex, okay? So it's, when you work with these sort of nilpotent groups, it's very hard to deal with the complete theorem because it has a lot of orders, and you kind of would like a homogeneous differential. So if you shave off a few differential orders, then it's better, okay? So you would like a sharper subcomplex. So when you consider the Rumin construction, this is limited to using homogeneous weights. However, the other construction, so with the BGG construction, is not limited to that. So it is more open to be applied to a more general setting. Yeah, thank you.